Hi, it's your old chemistry teacher, Mr. Springer again, and I thought I'd give you a little short video on the gas laws. It's possible your teacher may want you to know the names of the laws and what they stand for. So the first one here I've got is Boyle's law, and Boyle's law says that pressure times volume is a constant. And the funny thing about this constant, for every sample of gas, every trapped gas sample that you might have, the constant is going to be different. It'll stay the same for that particular sample, or whatever you do to it, but it varies from sample to sample to sample. The easiest way to do problems with this is P1V1 equals P2V2, and we'll see that they are inversely proportional. That means if one goes up, if pressure goes up, then the volume has to come down. Okay, so that's Boyle's law. Pretty simple at that point. Charles' law says that volume divided by temperature is a constant. And again, it's one of those variable constants that changes from sample to sample. When you're doing math of this, though, V1 over T1 equals V2 over T2, and those are directly proportional. The third one that you might run across is gay-Lussac's law. It says pressure over temperature is a constant. Again, notice it's the crazy mixed up constant that changes every time, but for each sample it will be the same. P1 over T1, P2 over T2, again directly proportional. When pressure goes up, temperature goes up. With Charles' law, when volume went up, temperature went up. When volume goes down, temperature goes down. And so those two are kind of closely related. And then the next one you might run across, or it may come later, Avogadro's law. Remember, Avogadro is the guy that gave us the lovely number 6.02 times 10 to the 23rd. And so he was concerned with moles, V volume over amount, N, some people say that's number of moles, volume over amount is a constant, V1 over N1, V2 over N2. Again, directly proportional. One goes up, the other goes up. One goes down, the other goes down. And the last one that you have a name for is the combined law. And the combined law says pressure times volume over temperature is a constant. Again, not always the same. P1V1 over T1, P2V2 over T2. And this is pretty complicated in its proportionality because P is directly proportional to T as is V, but P and V are inversely proportional, so it's hard to really come up with a, you can't really say it's directly or inversely, it's kind of a little bit of both. So, there are those 5 gas laws. There's one more that you might be interested in. It would be nice if we could combine all 4 variables into the same law. And if that's the case, just like in the other laws, notice, if we've got a P or a V, it's on top. If we've got an N or a T, it's on the bottom. So, in all the other laws, P and V are always on top in the numerator of the fraction, and the T are on the bottom, which is the denominator. So, if we combine all 4, P times V over N times T would be a constant. But, since all 4 properties are involved, this is a real constant. It's the same every time. Every time it's the same. So, if we're looking at that constant, we're going to call it the universal gas constant, or sometimes it's called the ideal gas constant. And it is assigned the letter capital R. I've never had anyone give me a good reason for why it's R. It's R. So when we put it all together, P times V over N times T equals R. And since it's always the same, since R is a fixed constant, we ought to be able to calculate what the value of that constant is. So let's consider a gas at STP, which is standard temperature and pressure. Standard temperature, of course, 273 Kelvin, which is 0 Celsius. You've got to convert to Kelvin. Notice what would happen if we use Celsius and the temperature was 0. We put a 0 into this, what happens? It's not solvable at that point. We've got a denominator of 0. Everybody knows since, what, 4th, 5th grade, you can't put 0 in the denominator. You can't divide by 0. So we have to put everything in Kelvin. Plus you could have negative temperatures in Fahrenheit or Celsius, and then this bottom would be negative, and then you get negative amounts of pressure or moles or temperature or what, or not temperature, volume. Then we can't have that. So we must use Kelvin. cannot go 0 or below. So standard pressure then, if you're using the SI unit, which is kPa, it's 101.3. If you're using atmospheres, which is my favorite, it's 1. If you're using millimeters of mercury, which was the first one that was invented, it's 760. And if I can get you to remember that 1 mole of any gas at STP has a volume of 22.4 liters. Well, how does that affect things? Well, let's plug in what we know and solve for R. So PV over NT equals R. We're going to plug in 101.3 kPa for pressure, 22.4 for volume, 1 mole for N, and 273 Kelvin for T. And what we should get, let's see here, 101.3 times 22.4 divided by 1 divided by 273. Remember, if it's in the denominator, we're dividing. If it's in the numerator, we're multiplying. And I get a number 8.31. Now, if your teacher is wanting you to do well in life, they will make you put units on these R values. I like to use liters, kPa, per mole, Kelvin. Okay. What if we wanted to find out what that is in atmospheres? Well, we just do the same thing, only we're using 1 atmosphere rather than 101.3 kPa. So it's basically at this point just 22.4 divided by 273, and I get, oops, 22.4, 273, 0.082051282. How about 0.0821 liter atmosphere per mole Kelvin. If we're doing millimeters of mercury, or torr as it's sometimes called, named after the guy who invented it, Torricelli, we got 760 in place of the 1 atmosphere or the 101.3 kPa. So we're just going to do that math. 760 times 22.4 divided by 273. 62.35897. I'm going to call it 62.4 liter mmHg per mole Kelvin. The way I've always seen the ideal gas law presented is in this form: PV equals nRT, and you can find all the other gas laws in that when we put it in this form. Right, we're just rearranging, solving for R. Take the N and the T, dividing PV by N and T. So we have all the other gas laws right here. Look, if we cover up the denominator, P times V, well, that's Boyle's law. P times V is a constant. If we want Charles' law, V times T is a constant. That's Charles' law. Gay-Lussac's law, P over T is a constant. That's Gay-Lussac. And Avogadro, V over N is a constant. So if you know this relationship or this relationship, you can find all the other gas laws. It won't tell you the names. You're just going to have to memorize those names if you need to know them. But otherwise, this will tell you how to solve the problems, where to start, and that sort of thing. So, I hope this was helpful. I'll be back with another video where I show you how to solve some problems using these gas laws. See you next time.